Okay, let's dive right into this. Imagine for a moment a master jazz musician. Think about it. When they step out onto that stage, the lights hit them, the crowd goes quiet. They actually don't know exactly what notes they're going to play. They improvise. It's totally off the cuff. But here is the absolute crucial secret. They can only improvise brilliantly because they have spent literally thousands of hours rigidly mastering the foundational rules of music theory. They know the scales inside and out. They know the chords. They know the exact structure. They have to know the rules perfectly before they can break them creatively. Passing your Cambridge Physics Paper 5, specifically focusing on experimental skills and investigations, but honestly this is equally applicable to all the foundational Cambridge syllabuses like 0625, 0652, 0654, 0972, 5054, and especially that advanced 9702 level, is exactly like playing jazz. It requires you to improvise, but within a very, very strict structure. Let me introduce you to two specific types of students we see every single year in the grading room. First up, we've got Alex. Now, Alex is brilliant at memorizing facts, just an absolute machine. But when faced with a practical exam question, Alex completely overloads the page with raw physics knowledge, just throwing every single equation, every textbook definition at the wall, but providing zero actual analysis of the experiment at hand. Red marks everywhere. Then we have Sam. Sam genuinely understands the concepts, but Sam rushes. Sam is always watching the clock, completely missing the specific command word requirements, skipping over vital safety protocols, and just hemorrhaging easy marks. Both Alex and Sam are working incredibly hard, but they're basically playing the wrong tune. Today, we're going to completely fix that.
So, this brings us to the ultimate question, and frankly, it's the primary fear I hear from students literally all the time. How on earth do you prepare for an experiment you have never ever seen before? It's terrifying, right? You flip open paper 5, your heart is pounding, and the examiner is asking you to investigate something incredibly obscure that was definitely not in your textbook. Alex completely freezes here. You know the feeling, trying desperately to remember if this specific setup was hidden in chapter 4 somewhere. Sam, on the other hand, just starts writing a generic, rushed method without actually reading the prompt carefully. But I want to validate your fear right now. It is completely normal to feel intimidated by this. However, the secret to mastering this paper is not photographic memorization. Let me repeat that. It's not about memorizing every experiment that has ever existed. It is about relying on a repeatable framework. The Cambridge examiners do not expect you to have seen the specific experiment. They fully expect you to know how to approach any experiment. They're testing your structured thinking. They're testing your blueprint. Before we continue building that blueprint, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get into the structure. So here is our roadmap for completely demystifying the 30 marks of Cambridge Physics Paper 5. We're going to cover 4 key areas today. Number 1, blueprinting your investigation. Number 2, visualizing data. Number 3, mastering uncertainties, which I know for a fact is a massive pain point for so many of you, but we're going to make it easy. And finally, number 4, we'll bring the whole shebang together into the physics blueprint. All right, let's move right into our first major section, blueprinting your investigation. Question 1 of the exam is worth 15 marks. That is literally half of your entire paper, and it focuses entirely on planning your unseen experiment. Top-tier students, the ones getting those A stars, they don't just randomly list steps. They rely on a highly structured approach to hit exactly what the assessment objectives demand. Let's look at the actual skill areas the examiner is actively hunting for. The examiner is looking for 4 strict skill areas when you blueprint your experimental plan. Think of these as non-negotiables. Step 1, define the problem. Step 2, method of data collection. Step 3, method of analysis. And step 4, additional detail and safety considerations. Again, think back to our jazz musician. This is your sheet music. If you skip a section, the whole song falls apart. You literally cannot just jump into listing your apparatus without first explicitly defining the problem. This is exactly where Sam usually loses a ton of marks, by rushing straight into step 2, just listing out beakers and wires. You have to force yourself to pause, take a breath, and systematically work through these 4 stages in order. Let's break down exactly what step 1 looks like. Defining the problem is all about variables. If you don't nail this, nothing else works. You absolutely must write down these 3 crucial variable types clearly on the page. First, the independent variable. This is the one you, the experimenter, deliberately change or control. Second, the dependent variable. This is the one that changes as a result of you tweaking the independent variable. It's the thing you are actually measuring. And finally, control variables. These are any other factors that might affect the experiment, which you generally must attempt to keep perfectly constant. Let's do a live transformation here to see this in action. Imagine an experiment about how the thickness of insulation affects the cooling rate of warm water. Okay? Alex, our overthinker, would write a massive paragraph about the complex laws of thermodynamics. Result? 0 marks. Sam, rushing as always, would just scribble down, measure the water. Maybe they get 1 mark if the examiner is feeling generous. But a top student? They write it out clearly and concisely. Independent variable, thickness of insulation. Dependent variable, temperature change of the water per unit time. Control variables, maintaining the exact same starting mass of water and keeping the surrounding room temperature completely constant. Boom. Clear, structured, 0 fluff, and instantly picking up the maximum marks. Now, let's look at how mechanical this gets as we move into the actual method. Once your variables are totally locked in, you move to data collection and additional details. Here are your absolute must-haves if you want those top grades. First, a clearly labeled diagram of the arrangement of your apparatus. Seriously, do not write a massive confusing paragraph describing the setup if a simple, clear diagram can do it 10 times better. It saves you precious time and totally avoids ambiguity for the examiner. Second, you have to explicitly explain how you will vary the independent variable. Don't just generically say, change the thickness. Say exactly how. Vary the thickness by adding successive layers of insulating material and measuring the new diameter with vernier calipers. See the difference? It's all about precision. Third, you need sensible, realistic safety precautions to minimize risk, not just be careful, something specific to the apparatus. And fourth, give exact details of your measurement techniques. This includes the range of meters you're using and details of any repeat readings. Remember, precision is literally everything in physics. If you don't say you're repeating readings to find an average, you're leaving marks on the table.
I really want to pause on this quote directly from the Cambridge Study Guide because it is so incredibly important for your mindset going into exam day. It is unlikely that you will be given an experiment that you have met before, so do not be put off by something that seems unfamiliar. Unfamiliarity is literally part of the test. They are deliberately testing your nerve just as much as your physics knowledge. They want to see if you can rely on your blueprint when faced with the unknown or if you're going to panic. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's shift gears now and look at the second half of the paper where the math gets a bit more intense. Welcome to Question 2, Visualizing Data. This section is worth the remaining 15 marks of your paper, and it focuses heavily on data analysis, tables, graphs, forming conclusions, and overall evaluation. As we look at the data coming up today, I want you to mentally challenge yourself to spot the core trends before I even point them out. Let's dive straight into the core mathematical trick they absolutely expect you to perform. Okay, look closely. Here is the absolute core of Question 2 data analysis. The examiner is almost always going to give you a complex exponential or power law physics equation, and your main job, you have to force it into the simple, linear, straight line equation we all know and love from basic math, y equals mx plus c. Let's look at this text comparison on the screen. Imagine they hand you an equation like y equals a e to the power of kx. How do you graph that directly? You can't. Well, not easy. It's a curve. It's incredibly difficult to analyze or pull accurate constants from. So, what's our toolkit? Natural logarithms. By taking the natural logarithm of both sides, that scary equation translates into ln y equals kx plus ln a. Now mentally map that directly onto y equals mx plus c. It lines up perfectly. Your y-axis on the graph is going to be your ln y values. Your x-axis is just x. Your gradient, the slope of the line, m, is simply the constant k. And your y-intercept, where the line crosses the axis, your c, is ln a. You have just taken a complex physics relationship and beautifully turned it into a straight line, where the gradient and intercept give you the exact constants you need to find. This isn't just a neat trick. This is a guaranteed skill you must master for this paper. Let's look at exactly how this plays out with a real worked example from the source material. Look at the table data here. They have given you the thickness of insulation, which is x, and the rate of temperature fall, which is delta T over delta T. Imagine Alex in the exam room. Alex panics, doesn't use logs, and just plots the raw temperature fall against thickness. What happens? They get a messy curve. They lose all the subsequent marks because they cannot easily calculate a straight gradient to find the constants. Instead, look at the final column in that table. The smart student has calculated the natural logarithm of the rate of temperature fall. And when you plot those log values against the thickness, x, on the graph below, look at that. It's a beautiful, clean, straight line with a negative gradient. By simply choosing 2 points on this line, let's say, for example, the points 1.0, negative 2.96, and 7.4, negative 3.80, you can easily calculate the slope, rise over run. In this specific case, the gradient is negative 0.13. And from our previous slide, remember the mapping?
We know the gradient equals k. So just like that, k equals negative 0.13 inverse centimeters. This is the exact, repeatable process you will follow every single time they give you an exponential relationship. Okay, take a deep breath, shake out the tension. We are now tackling what is widely considered the absolute most intimidating advanced technique of Paper 5, calculating absolute uncertainties and plotting error bars. I know students dread this. Do not let this freeze you. It is literally just another set of rules to practice. Once you see the matrix of how it works, it genuinely becomes free marks. Let's break it down. So the most crucial point here is how we handle raw data uncertainties when we transform them. Look at the data table on the left side. You are given a value for d, which is the diameter of a diffraction ring, and it has an absolute uncertainty of plus or minus 0.2. But remember our trick. You aren't plotting d on your graph, you are plotting the log of d. So how on earth do you find the uncertainty for that new log value? You can't just write plus or minus 0.2 anymore. You actually have to calculate the log for the recorded value, and then calculate the log for either the absolute largest or absolute smallest possible value in that initial uncertainty range. The difference between those two new log numbers is your new absolute uncertainty. You must calculate this specifically for every single row in the table. Once you have those specific numbers, you plot them visually as error bars. Those are those little vertical or horizontal lines you see passing through your data points on the graph on the left. They represent the window of doubt for every single measurement. So I have a challenge for you. Think about this for a second. If you had to concisely explain how to draw the worst acceptable line using those error bars, what would you say? How do you define it?
And here is the exact answer to that challenge, pulled directly from the Cambridge Study Guide. The worst acceptable line is the line that has either the maximum or the minimum gradient and goes through all the error bars. This is a vital tip to memorize. On your graph, you're going to draw your normal, beautiful line of best fit right down the middle of the points. But then you deliberately draw the shallowest or steepest possible straight line that still physically touches every single error bar you plotted. That is your worst acceptable line. It physically represents the extreme boundary of your experimental error. If you don't draw this line accurately, you literally cannot calculate the uncertainty in your gradient later on.
Let's map this out chronologically because it is a very rigid, non-negotiable 4-step process. Step 1. Calculate the gradient of your normal line of best fit using 2 points that lie exactly on that line. Step 2. Calculate the gradient of your worst acceptable line, again using 2 points specifically on that new extreme line. Step 3. Simply find the difference between those two gradients. Step 4, that difference, that is your estimated final absolute uncertainty for the gradient. You then repeat this exact same 4-step process for the y-intercept. Find the best fit intercept, find the worst acceptable intercept, and find the difference. It feels super tedious, I know. Sam totally hates this part because it takes patience and meticulous calculator work. But Alex actually excels here if he remembers the steps, because it's purely logical. If you practice this exact timeline just 5 times before the exam, it will literally become pure muscle memory. All right, let's move to our final section and bring all these isolated concepts together for the grand finale. We have decoded the command words, we have systematically planned the data collection using clear variables, we have visualized the data linearly using logarithms, and we've just conquered calculating uncertainties. What we have built together today is the physics blueprint. 30. That is the magic number. That is the total number of marks available on Paper 5. And I'm telling you right now, it is entirely possible to get 30 out of 30 if you strictly apply the 3 rules of our system that we've been talking about. Rule 1, command word decoding. Give the examiners exactly what they ask for. Nothing more, nothing less. If they ask to state, just state. If they ask to explain, use your Peel framework, point, evidence, explanation, link. Rule 2, structured planning. Systematically define your independent, dependent, and control variables on paper before you even think about touching the apparatus or drawing a diagram. Rule 3, the time management matrix. Pace yourself. Do not spend 45 minutes making a beautiful diagram for question 1 and then leave the math in question 2 completely blank. Balance is everything. Students who actively implement these specific physics strategies see an average improvement of 2 grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCS and click that bell. Don't let another exam pass you by without having the right strategy. Drop a comment below with your specific target grade for physics and the absolutely biggest challenge you're currently facing. Our team reads and responds to every single comment. Like and share this explainer with a study partner right now. Ace the Exams. Your Cambridge success starts here. So I leave you with this final provocative thought. When you finally sit in that exam hall, You open that paper and you see a completely bizarre, unfamiliar experiment, maybe about diffraction rings or thermal insulators you've literally never heard of. What are you going to do? Will you be like Alex and Sam? Will you let an unseen variable completely freeze you in a panic? Or will you step up, like the master jazz musician? Will you look at that blank page, smile, lean heavily on your structured blueprint, and improvise a brilliant, structurally perfect 30 out of 30 top mark answer? The choice is entirely yours, and the tools are now right in your hands. Keep studying smart, trust the framework, and I'll see you in the next explainer.